All right, today we're going to talk about wave-particle duality, and we're going to talk about those because we're going to get into talking about electrons, and specifically lab data that helps us understand what electrons do and how they behave. So specifically, wave-particle duality is looking at the two characters of light. We need to think of light a little bit differently than how we normally think about it in our day-to-day. It's a part of the electromagnetic radiation spectrum, and that's all light, including visible light. It's also light like X-rays and radio waves and microwaves and gamma rays, ultraviolet, infrared. And we have a way to remember that raging Martians invade Roy G. Biv using X-rays and gamma rays. So R is for radio waves, M is for microwaves, I is for infrared or inferior red, it's less than red. Then we have Roy G. Biv, which is visible light. U will be ultraviolet. X-rays, then it just says it, and then gamma rays. So this electromagnetic radiation has wave and particle characteristics. So that's the basics of light that we're talking about here. And then we have this spectrum. This is showing how what we just talked about looks like on a visual graphic. We have our gamma rays, which have high energy. They can hurt you. We have radio waves, which have low energy. These ones can't really hurt you. In the middle, this very, very small, very speck of the whole continuum here, of the whole spectrum, is visible light. But this is normally what we think of, and we have, again, Roy G. Biv. It's just backwards, Vib G. Yor. And this is the spectrum. So high energy, low energy. Then we have frequency, high frequency, low frequency, wavelengths, very small wavelengths, very high wavelengths. So that's the second set of our basics of light. Then we have electromagnetic radiation, which has, we can summarize it in this document right here. The short wavelengths have high frequency and high energy. They can hurt you. This is like gamma rays. The long wavelengths have low frequency, low energy, can't hurt you, like microwaves sort of. And then really radio waves really exhibit this set of properties here. High frequency waves are going to have this reoccurrence over a very small period or a very short amount of time, whereas low frequency waves have their wave repeat over a longer period of time. So this is a graphic showing what a wavelength looks like and what frequency looks like in terms of wavelength. How is this important to us in chemistry class? So in chemistry class, we can see electrons demonstrate characteristics of light, and they're both of the wave and the particle demonstrations of light. So one way that we can see that is by how electrons give off light energy. And now normally electrons are existing in what's called the ground state. That's where they normally live inside of an atom. But if they're struck with some energy, they can move to an excited state. And this is a high energy that isn't very stable, but when these electrons jump to these higher levels of energy, they have to jump to very specific levels. I like to think of it as an elevator. If you get in an elevator, you can go up that elevator, but you have to go to a specified set floor. You can't go in between two floors. The elevator doesn't allow it. And then you can travel to any of the floors that are above you. And then you could also go from floor 1 up to floor 3, or you could just go from 1 all the way up to floor 7. And likewise, when you come back down, you could go from 7 down to 5, and then 5 down to 3, or you go from 7 down to 2. So any way combinations, you can move these electrons just like you can move in a giant hotel inside of an elevator. So pictorially, it looks like this. The electron's normally in its ground state. So in this case, we're saying ground state is in energy level 1. If the electron's struck by some energy, the electron's going to go up into excited state. Now notice it's going up to energy level 2. Now this is unstable, so it's going to fall back down to its normal ground state, and in doing so, it's going to release a photon of light. So here's a particle of light, and that's part of why we're talking about wave-particle duality. And then we can see this particle of light in lab experiments, or if you're just looking at fluorescent light bulbs, you're seeing photons of light because of this phenomena. Electricity is the energy source exciting these electrons. Another example would be this electron can be in, again, ground state, energy level 1. They can get jacked up all the way to energy level 3. So this energy must have been a larger quantity of energy in order to excite the electron from energy level 1 all the way up to energy level 3. Now, when this electron falls back down, it has a couple of options. It could fall all the way from energy level 3 all the way back down to energy level 1, or it could fall from energy 3 to energy 2, then energy 2 to energy level 1. And that distance that electron falls is going to be related to the color of photon that we actually see. What can't happen is this energy strike and then get that electron in between two energy levels. That's not allowed. This electron can access either energy level 1 in this picture, or energy level 2, or energy level 3 in this picture, but it cannot access this non-existent energy level 2.5. We call that receiving quanta of energy. They can only receive specified amounts or quanta of energy. So these electrons that are falling back from excited state to ground state are releasing different colors of light. And we see a mixture of all those colors, and that's like these fluorescent tubes I was talking about earlier are showing a mixture of all colors, which is why we see white light. But sometimes we don't see white light. For example, if you're looking at a neon sign outside of a restaurant, you might be seeing red light or blue light. And what that means is that there's only a set number of photons that are being released, and those set number of photons make you see the color blue or the color green or whatever color you happen to be seeing. But in reality, it's not just one color that's coming out of that light source, or at least normally it's not. And because of that, we can actually look at the different colors that make up that mixture using something called a spectrometer. So how those work is light shines in this spectrometer, and this thing called grating or diffraction grating is going to take that light and split it into its components. Now, since this is white light, it has all the colors in the rainbow, but it doesn't have to have all the colors in the rainbow, this light, if it's not white light. This one has an orange, a blue, and a purple, and together they would make one single color that probably, well, is definitely not going to be white light. Now, these colors are again related to how much energy is being released. So if that electron is at a high energy level and it falls a long way, it has to release a lot of energy. A lot of potential energy is stored in that further out energy level, that excited state. So for example, this purple line is going to be represented by an electron that falls a long distance, whereas this blue line is going to be by an electron that doesn't fall as far, and this orange line is going to be represented by an electron that falls a very short distance. So the energy level of the electron determines the amount of energy that's released, which in turn relates to the energy of the color that we see. So light shows both wave and particle properties, and as far as light goes, we can talk about light in terms of frequency, which is a wave property. How often is that wave occurring? We can talk about it in terms of wavelength. How far does that wave need to travel before it repeats itself? And the evidence that shows us this was the double slit experiment, which wouldn't be described as light as a particle. It's only describing light as a wave. So the results of this experiment, which you can look up, and you could YouTube it, or you could just search it on Wikipedia or something, but you would see that the results of that experiment saying, hey, light doesn't work as only a particle. At least this experiment is saying that. We have an equation that fits nicely with the wave properties of light. It's C equals lambda V. So this weird looking letter here, that's the Greek letter lambda, and then V. So C is going to be the speed of light. That's a constant number. And then lambda is the wavelength, and it's going to be measured in meters, and it has to be meters because our speed of light is measured in meters. And finally, our frequency, V, is measured in hertz, or it's also called inverse seconds, 1 over S. And here's a conversion factor from converting from nanometers to meters, because when we normally measure light in our class, we're measuring in nanometers. So speed of light is equal to wavelength times frequency. This is a formula showing light as a wave. But we can also talk about light as a particle. So other experiments were saying, well, we can't just describe light as a wave. We have to also describe it as particles, because the results of the experiment just didn't come in line with light only acting as a wave. And that's because of these things called photons. And we were talking about photons when the electron was dropping back from excited state to ground state. The electron releases a photon of light. And these photons are just little tiny packages of light with a set amount of energy, but they don't have any mass, which was kind of a weird thing because particles have mass. So that's where this whole wave-particle duality issue comes into play. So the experiment that showed this was the photoelectric effect. And the basics of that is that light shines on a piece of metal, and when it does, if it's high enough energy light, it's going to release electrons in doing so. Now, the math that supports this is a formula E equals hv, where E is the energy of a photon, and h is Planck's constant, so that's a constant value again that you can look up in a book, times again the frequency. So the previous equation, C equals lambda v, is related to this one because they both have frequency involved. Now, E is energy in joules, measured in joules. H is Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. And finally, again, frequency is hertz or inverse seconds 1 over s. So what I think you should have learned after watching this video is that light has dual properties, both those of waves and of particles, and you learned the electromagnetic radiation spectrum. That's all kinds of light, including visible, but also gamma rays all the way through radio waves. You learned that this matters to us in chemistry because electrons behave also in a wave-particle duality, and we see the results of that when we see light being emitted by different light sources. And then finally, we have a couple equations that can represent both light as a wave and as a particle. Hope that helps.